Now that you guys have an understanding of how the transit method works, let's take a look at the Kepler Space Telescope, which to date is the telescope that we've used to find most of the exoplanets that we know of. Your Transit Tracks assignment asked you to find 2 mystery planets. First one, the mystery B planet, is actually Kepler 10b, and that is the first terrestrial or rocky planet that we ever found. Pegasi 51b was a gas giant. Kepler 10b is the first ever planet that you could theoretically land on, but it's very close to its host star. As you can see, it orbits in just a matter of days, so it's right next to its star, which means it is extraordinarily hot. If you were to land on the surface, it would be like landing in a sea of lava. Our first solid planet that we found is definitely not a planet that we could ever travel to, that we could ever land on. Mystery C is actually Kepler 453b, and this is a planet that is orbiting the first ever binary star system, where there's 2 stars orbiting around each other, and then the planets are going to orbit around both of them as though they were a single giant star. And Kepler 453b is the first ever planet that we found orbiting around a binary star system. If you were to travel there, you would see that there are 2 stars in the sky. So your sunset would look something like this, or maybe something like this. Or my favorite interpretation, something like this. I really hope you guys know what this is. If you don't tell me. As a hint, this gentleman right here is named Luke. A lot of times, you're going to have a star with more than one planet. So if you look over my head, that star has a bunch of planets. You can see that there are dips in the brightness depending on which stars go in front. And you can see that in this light curve, there are dips that actually dip down different depths. So you know that those are different planets. These are color-coded, so it makes it much easier. This one, though, happens to have a dip here and a dip here. This one repeats more often, so this one is a bigger planet. It dips farther down, but it also happens more often, so it's closer in. This is a smaller planet because it does not dip as far down, and it happens much less frequently. So you can tell that this particular star has got 2 different planets. We named them Kepler 9b and 9c. This is actually Kepler 11b, c, d, E, F, and G. This star has 6 planets, and I actually split them into 2 different graphs to make it a little bit easier to see, and then they color-coded it, which makes it even easier to see. You can tell that there's a dip that goes here, there's a dip that goes to this depth, and then there's a dip that goes to this depth. So this top graph has got 3 planets causing those dips, and then you have 1, 2, 3 in the bottom. If you were to put all of these together, it gets a little bit messy. If you have a computer, it's very easy to distinguish the depth of all of these dips, and you can tell that there are 6 planets. As a review, different size planets are going to cause different size dips, but it also depends on the size of the star itself. So this smaller planet, smaller than this one, causes a bigger dip because this star is smaller. And because the star is smaller, this little planet is actually covering up a bigger percentage than this planet is. So the dip is going to go farther down. And these are some of the actual, and Kepler 4, 5, 6, 7, those are some of the planets that you guys got to study in that transit track activity that you just completed. So these planets look little, but when you compare them to our solar system, many of them are bigger than our biggest planet. Jupiter would be about this size, Kepler 6, 8, 5, 7. So a lot of the ones that we just looked at on the previous slide are much bigger than Jupiter. Here's another question for you. Why do you think these planets, like this is a green planet and a red and a blue and a yellow, why are those planets, why do they look like bouncy balls or balloons? Why don't they look like an actual planet? Why would NASA put out a poster with a bunch of planets that look fake? Obviously, because we don't know what the planets look like, all we see are the dips. We don't have actual close-up photography of these planets, so we have absolutely no clue what they look like. And NASA just decided to put a sphere instead of trying to make up a random looking planet. We do have to be careful sometimes when we are seeing those dips. I mentioned that a lot of stars happen in binary systems, where one star is much brighter than the other star. And if you have a super bright star that's all of a sudden covered up by the dim star, that dim star is going to block light from the bright star, and the overall amount of light that we see is going to go down. And a binary star system, they're going to orbit, which means that's going to repeat. We need to be extra careful that when we see a dip in a star's brightness, that is a planet instead of just a binary star system where the stars are different brightnesses. When we see something that we think might be a planet, we look a little bit closer with other telescopes to make sure that it's not just a binary star system that we're mistaking for a planet. Let's take a look at the telescopes that are finding all of these planets. The Kepler telescope has found more exoplanets than everything else put together, basically, which is why so many planets are named Kepler 5b, Kepler 6b, etc., etc. They're named after the telescope that found them. Kepler, the space telescope, obviously named after Johannes Kepler, the scientist, was launched in 2009. It cost about $500 million, and it doesn't work anymore. It lasted roughly a decade. Its mission is done here in 2020. It actually ended a few years ago. This is what Kepler did as it was up in space. It actually did not orbit Earth. It followed Earth like a little lost puppy. And a lot of people ask why we didn't just put it into orbit. And the reason is that you'll notice that it is always looking at the same part of the sky. You have to look at these stars continuously to see if the brightness dips. Because if all of a sudden you look at a star and then look away, you might miss a planet going in front of it. So Kepler has to always look at this section of the sky, and if it orbited, there would be many times where it's behind planet Earth, and it would not be able to see those stars that it's studying. So we had to put it behind planet Earth so that Earth never got in its way. We didn't miss any of those brightness dips. You'll also notice that it keeps spinning. I'm wondering if you guys can figure out why it keeps spinning. If you look closely, there are solar panels on one side of the telescope. Obviously, it needs to continuously turn in order to... You need to continuously turn in order to have electricity be produced. The problem is that in order to turn, you have to have gas, which will be expelled to turn the telescope, and it ran out of gas. You've seen this slide before. How many planets has Kepler found? Well, when I started this class back in 2014, about 250 that were confirmed. Candidates, about 3,500. And that has gone up over the years until 2020, 4,307 exoplanets, with another 2,428 that are candidates. Where is Kepler looking? Where are we looking? The stars that are close enough to us that we can actually determine that dip in brightness, all of them are inside of this little circle. About 300 light years is the maximum distance. All of the planets that we have found so far, the thousands and thousands and thousands that we've found, every single one of those is inside of this little tiny itsy bitsy circle in our own galaxy. And this is actually a little bit misleading because this makes it look as though we are looking in all directions. However, Kepler is only looking at one spot in the night sky. It's only looking in one direction in an area of the sky which is roughly the size of a full moon. So there might be planets, this is the full moon, there might be a bunch of planets right off to the side that Kepler is never seeing. We didn't want to move Kepler to look over there. We didn't want to move Kepler to go look at another part of the sky, because then it would obviously miss the brightness dips that are occurring. This is an important slide. It's got a lot of information that you're going to need to have in your brain. How are these discoveries made? Right off the top of your head, you already know. When a little planet goes in front of a star, it causes that star's brightness to dip, and we can detect that particular drop in brightness. But it's not a video camera like what these make it seem. Instead, Kepler takes a picture every 30 minutes. It takes a picture of the sky, downloads it to Earth, and then a computer will go through and compare that to the last picture to see if any of the tens of thousands of stars that are in that field of view have decreased in brightness. So it's not a video as these often make it seem, but it's instead a picture taken every 30 minutes. How far down it goes, that's the size of the planet. How often it happens, that's the orbital period. If we know its orbital period, we can determine its distance. If we know its distance, we can determine if it's in the habitable zone, which we will get to in a few days. So we get a lot of information just by these little dips in brightness. Now going back a slide or two, what is the difference between a confirmed exoplanet and a candidate exoplanet? In order to be confirmed, you have to have seen the brightness dip 3 times. 1, 2, 3. If you've only seen one brightness dip, maybe it was an asteroid that flew by. Maybe it was a cloud of gas and dust that passed in between that star and the sun. Maybe it was something other than a planet. Obviously, you have to wait for another brightness dip. What if you have a brightness dip of a certain depth, and then, 10 days later, you have another brightness dip? Does that guarantee that that is a planet? Likely, that's where you're going to make it a candidate, because you have one dip, and then you have another dip that matches, and you're like, that might just be a planet. So how can you be sure? Well, if that's a 10-day time span, you wait 10 more days. If that dip happens the 3rd time, you have confirmed that that is in fact a planet. So why are there still so many candidates? Why are they not confirmed? Why haven't they found that 3rd dip? Well, think of our own solar system. We just launched Kepler in 2009, 12 years ago. It takes Jupiter 12 years to orbit once. Let's say we're an alien and we're looking at the sun. We would see Jupiter go in front of our sun. That's one. 12 years later, it would go around for the 2nd time. We're like, hey, there's another dip of the same size. Maybe that's a planet. Let's put that on the candidate list. And we have to wait another 12 years to get that 3rd dip. Right now, Jupiter would not be considered an exoplanet. Is it a planet? Of course it is. But if we were an alien looking at the sun, we would not consider Jupiter a planet yet. 12 years from now, we would. It takes Saturn 29 years to go around one time. So let's say we got lucky and saw Saturn go in front of our sun one time. We would still be waiting for that 2nd dip. It would still be considered a candidate. So basically, the difference between a confirmed exoplanet and a candidate exoplanet is that we need more data. We have to continue to look at these stars to make sure that that dip happens again for a total of 3 times. After 3 times, if they all match, we can confirm that it's an exoplanet. Otherwise, we consider it a candidate planet. So why would aliens not consider most of our planets in our solar system actual exoplanets? Back in 2012, we only had a couple dozen actual planets, but they put them next to our solar system's planets. So here's Neptune, there's Jupiter, there's Earth. Only one of them is actually smaller than Earth. Every single other planet that we had found up to that point was bigger than planet Earth, and they all look like bouncy balls. And the reason is that we don't know what they actually look like. Why do you think NASA was finding big giant planets, not little tiny planets? The Kepler mission actually ended 2 years ago in 2018. K2 is the 2nd half of the Kepler telescope's mission. There's still quite a bit of data that we have to go through, which is why we are continuing to find planets that were found by Kepler. So in almost a decade, Kepler looked at 500,000 stars, confirmed 2,600 planets, and there's been almost 3,000 scientific papers published from this one telescope. Now that Kepler is done, are there any other telescopes looking for exoplanets? What about those planets that have only crossed once or twice, we're still waiting for that 3rd dip in brightness? Anybody still checking up on that? Yeah, there are a bunch of other telescopes that are currently looking for exoplanets. Many of them are on the ground, like all of these. Many of them are up in space. Space telescopes work way better because we don't have to worry about refraction of any of the light from our atmosphere. HAT, which is a Hungarian telescope, gets this data, and they had to fit a best line through their data, whereas Kepler up in space had this data. It's much cleaner, it's much more accurate. All of this extra noise is simply from our atmosphere. So sending things into space makes it much easier to find these planets. This bottom one down here, TESS, which stands for the Transiting Exoplanet Survey Satellite, is what NASA currently has going on. It was launched right when Kepler stopped working. TESS is currently looking at stuff that is in the southern half of the celestial sphere. Kepler looked at stuff that was in the northern half, and TESS is looking at stuff in the southern half. But TESS can actually change where it's looking at.
In the last few decades, we have found thousands of worlds around other stars. A new NASA astrophysics mission will help us find many more.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across all sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
During its 2-year survey, TESS will look for signs of planets, ranging from Earth size to giants larger than Jupiter. TESS will search for these new worlds, or exoplanets, using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TESS can detect those subtle dips and even use them to determine some basic features of the planets, such as their size and orbit. Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky, called an observation sector.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
TESS will watch each observation sector for about 27 days, before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS will fly in a highly elliptical orbit that maximizes the amount of sky the spacecraft can image, and is carefully timed with the orbit of the Moon. It will spend most of each 13.7-day orbit collecting data, and then, as it passes closer to Earth, it will transmit that data to the ground. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets. Since most of the exoplanets found by TESS will orbit bright stars, missions like Webb will be able to measure the spectra of starlight absorbed by the planet's atmospheres, which can indicate what they're made of. Ground-based measurements of the TESS exoplanets can determine their masses. Combining the masses with TESS's size measurements reveals densities, allowing scientists to better understand the exoplanets' compositions.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Kepler. So TESS is going to take that same search approach, but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when searching for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at things like planet composition and atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are even further away and in deeper parts of the galaxy as well.
TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own.
TESS has a lot more cameras on board. With better optics, a wider field of view, TESS is going to be able to look at a lot more stars and hopefully find a lot more planets than Kepler was able to. Right now, TESS is looking at the southern part of the sky, and it's going to eventually start looking at the northern part of the sky. Our goal is to have TESS find somewhere around 30,000 exoplanets in just a couple of years. Kepler found just under 3,000. More might be coming because of the candidates, but TESS, because it's looking at such a huge area of the sky, and it can move and look at different areas of the sky, is hopefully going to find about 10 times more than Kepler is. So what are the implications of Kepler? Well, first, finding exoplanets is cool. But Kepler, using the transit method, as it went on, was actually able to show that smaller planets with rocky surfaces are more common than the big giant gas planets. But what are the implications of that? Well, if the majority of planets have a rocky surface that you could land on, then they could possibly have liquid water. Then they could possibly foster conditions where life could happen. If every planet that we ever found was a big gas giant, the chances of finding life there is pretty small. But if the majority of planets that we keep finding are rocky planets, which is what Kepler is showing us, the chances of finding life go up considerably. So finding these planets that are roughly the size of Earth are basically the key to finding life somewhere out there in the solar system. The key to finding aliens.
NASA's Kepler mission has discovered the first Earth-sized planet orbiting in the habitable zone of a star outside our solar system. The newly discovered planet is called Kepler 186f and is about 10% larger than Earth.
Kepler 186f is the first validated Earth-sized planet in the habitable zone of its star. It's the outermost of 5 planets to orbit a star that is smaller and cooler than the Sun. This planet orbits its star every 130 days, and so this places it in the habitable zone, where it's in a region where it could have liquid water on its surface.
Kepler 186f resides in the Kepler 186 system, about 500 light-years from Earth in the constellation Cygnus.
This planet, Kepler 186f, orbits a star that's cooler and dimmer than the Sun. So while we may have found a planet that's the same size as Earth and receives a similar amount of energy to what Earth receives, it orbits a very different star. So perhaps instead of an Earth twin, we've discovered an Earth cousin.
On the surface of Kepler 186f, the brightness of its star at high noon is only as bright as our Sun appears to us about an hour before sunset. Scientists believe Kepler 186f is likely to be a rocky world, but are unable to confirm its mass and density.
This is one of the big milestones that we've been looking for in our attempts to find out if there are places just like home and if there's life out there. One of the big steps is to say, is there somewhere that looks, to all intents and purposes, like Earth? Well, we don't know just yet, but we know that there are places that at least look similar.
Managed by NASA's Ames Research Center, the Kepler mission collected this data using a space-based telescope to search one part of the galaxy for potentially habitable planets.
The first Earth-sized planet where we could actually land on it and not be crushed by the gravity orbits a red dwarf star. It's cooler, which means the light that it gives off is red, so if we were to land on it, the night sky would actually be kind of like a sunset. It would be a permanent sunset, red in color. And if you remember why our plants are green, because our sun gives off mostly green light, the plants there would be red. And in 2015, we found Kepler 452b, which is to date still the most Earth-like planet that we've ever found. Not only because of its size, it's virtually the same size as Earth, just 10% bigger, but it also, almost more importantly, orbits a star that's just like our sun. So it's going to get the same type of light that we get here on planet Earth. It's going to be the same distance away, which means a year is going to be the same amount of time. If we were going to go somewhere and be able to live just like we do on Earth, this is the planet that we would go to first. Turns out that actually our closest star to us, one that's 4 light years away, Proxima Centauri, has a planet that goes around it. The closest star to us has an Earth-sized planet that's in the habitable zone. And because Proxima Centauri is a red dwarf, it's a very cool star, so its habitable zone is right next to the star. So if we were going to go anywhere first, we would stop here to see how things are. It's Earth-sized, it's in the habitable zone. The problem is that because it's so close to its star, the amount of solar wind that comes off of the star would strip away any sort of atmosphere that might be there. It's about 2,000 times stronger than our sun's solar wind when you're that close. It's also right next to the star, which means two things. It's going to be tidally locked, so the same side is always going to face the star and get superheated, and the other side will be frozen solid. And any CMEs or solar flares that shoot off is going to go right down to the surface and sterilize the surface, making any sort of life impossible. If you add those three things together, it's tidally locked, so the same side is always facing the star. And if you want to have any sort of energy for life, you're going to have to be on the side facing the star. The solar wind is going to strip away any sort of atmosphere, which means any sort of solar flare or CME is going to get right down to the surface and completely sterilize the planet. So it's in the habitable zone, it's the size of Earth, it's the closest planet to us, but there's no way that there's going to be any life on it. There's no way that it's a habitable planet because it's so close to the star. And even still, if we were to get into a rocket ship and blast it off as fast as we could go, it would still take us about 80,000 years or so to get there. Probably not going to show up anytime soon to Proxima Centauri b. We also, a few years ago, found the TRAPPIST system, which is a planet about 40 light years away, and it has 7 planets, and all 7 of them are in the habitable zone, which is kind of cool to think about. If you could have 7 planets in the habitable zone around one star, think of how many other planets could be in the habitable zone of other stars. There's got to be aliens. There has to be. There has to be. KIC 8462852 just rolls right off the tongue. This is also known as Tabby's star because the astronomer who found it, her name's Tabby. And this has been in the news quite a bit. In fact, if you just type in Tabby star, you're going to get hundreds and hundreds of news articles that pop up. Why? Because scientists think aliens could live there. Why would scientists possibly think aliens live there? About 1,400 light years away, and we have these dips in the brightness. And you'll notice that's pretty regular. So they were looking for that third dip, and that third dip never actually showed up, which is unfortunate because this star had a candidate planet if they had had a third dip, which never showed up. And all of a sudden, years later, what the heck is going on here? This giant dip, and then nothing at all. Just nothing and nothing and nothing. And then this craziness happened. So we thought there could be a planet, and then we were disappointed and there's not, and then what the heck, and then even more what the heck. We have no clue what's causing those dips, and over the course of about 120 years, they've taken a look at very old photographs. It turns out that this star, over the course of 100 years or so, has gotten dimmer and colder. And stars do that when they age, but it takes millions and millions and millions, if not billions of years. This star did it in a little over 100 years. We have absolutely no known physical process that could possibly cause a star to get dimmer that fast, other than an alien civilization building a giant Dyson sphere, which is a big sphere that contains an entire star so that they can put solar panels on it and they can power their civilization. That's the only possible explanation that we can come up with, because there's no physical explanation that would explain why this star is acting like this. The brightness dips don't make any sense. The fact that it's getting colder and dimmer doesn't make any sense. It doesn't emit infrared light. Never seen a star do that before. What else could it possibly be other than aliens? It's aliens, right? Aliens are always the first answer in the news whenever astronomers say they can't explain something. As much as I want there to be aliens, jumping to that conclusion is not very scientifically responsible.
KIC 8462852 might sound like a randomly generated password to you, but I'm willing to bet if you've watched this channel long enough, you've actually heard it before. It's the name of a star, also known as Tabby's star, and it set the internet ablaze a couple years back when it dimmed in ways nobody could really explain, unless you pinned it on aliens building massive structures to power their civilization. Since then, though, we haven't seen the star's light fade, and so public interest in it did. But in April of 2017, light levels started dropping again, giving astronomers new clues to come up with new ideas. Are any more compelling than a giant energy-harvesting megastructure built by aliens? I'll let you be the judge of that. First, a refresher on why Tabby's star is so mysterious. In 2011, the Kepler Space Telescope observed its light dimmed briefly by 15%. Almost 2 years later, it temporarily dimmed again, this time by about 22%. Often, a drop in a star's light levels is a sign that a planet is passing in front of it, but even a planet the size of Jupiter would only block about 1% of the light coming from a star like this. And the dimmings caused by planetary transits should be symmetrical and at regular periods, but these aren't. They're erratic and all over the place and can last anywhere from 5 to 80 days. What we have on our hands, gang, is a mystery. An early explanation from 2015 was comets were knocked out of their orbit by a nearby star, and as they plummeted towards Tabby's star, they collided and created a debris cloud. At the time, that was the best-fitting solution that didn't involve a Vogon constructor fleet. Since that idea was first put forward, astronomers have taken a look at the data going all the way back to the 90s, the 1890s that is, and it turns out the star isn't as bright as it used to be. As you'd expect from a star this uncooperative, it's faded erratically, but overall it's dimmed 16% in the last century. Comets can't really explain the long-term dimming, so that idea is pretty much out. But maybe the slow fade is evidence of something else. Some of the first explanations proposed dust from early planets forming could be the cause. But Tabby's star is too old to just be forming planets now. One idea put forward in 2016 is kind of the opposite. Instead of a new planet, what we're seeing is the aftermath of an X-planet, one that crashed into the star about 10,000 years ago, causing a flare-up that the star is slowly coming down from, like a long, drawn-out belch. That could account for the long-term evidence, while orbiting remnants of the planet cause the more dramatic short-term drops in brightness. After this latest dip, yet another idea has emerged. What if it's a really big planet with some buddies? Trojan asteroids are rocky bodies that share the orbit of a planet. They hang out in Lagrange points, where the gravitational forces between the star and the planet are balanced. Jupiter has big groups of Trojan asteroids, so we've seen the phenomenon happen before. Maybe the Trojans caused those erratic dips, and the massive planet caused some of the more regular ones. For this explanation, the planet would have to be about 5 times the size of Jupiter, though, and Jupiter is just about as big as a planet can get before it starts fusing hydrogen and becomes a star. But the nice thing about this idea is it makes a prediction. If it's true, the Trojan asteroids will transit again in 2021, followed by the gigantic planet in 2023. Until then, we're just going to keep our eyes on the skies in case KIC 8462852 decides to do anything else weird.
If you have any other questions, I super highly recommend just Googling it, and you will get tons of information about Tabby's star. It's quite fascinating. And now I'd like you to go back into your science journal and answer these 2 questions that you wrote down last week. With aliens on it. Who knows?